Okay, increasing the complexity of what we're doing is now we have 3-point charges, but to keep it simpler than it might be, we'll have the 3-point charges in a line. So let's draw 3-point charges all in a line. And we'll call them, label them Q1, Q2, and Q3. And we could give them any signs we want. Let's give them a plus, and a minus. My drawing's not great today, but anyway. So now each point charge has a force on it due to 2 other point charges. So if we're going to look at the force on Q1, there would actually be 2 forces acting on it. There would be a repulsive force from Q2. I'll draw a vector. And that would be labeled, I'm going to have to squeeze this in, F of 2 on 1. So we give it the direction from the situation. It's in the negative direction, even though both charges are positive, just because of the way it's set up. And the negative charge, Q3, is exerting a force on Q1, but it's going to be an attractive force. So that force is in the positive direction, even though the charge is negative, just because of the situation. And I'm going to draw this arrow a little bit smaller. Actually, it should be much smaller. Let me erase that. And go back and redraw it, because according to this it should be quite a bit smaller. So I'm going to just make a very short arrow, and that would be the force of 3 on charge 1. And so if we wanted to know the total force on Q1, we would have to add those 2 vectors in the opposite direction. And you can see that the Q2 force is bigger because it's closer, and the Q3 force is weaker, and the total sum of the forces, on charge 1 are going to be equal to the vector force of 2 on 1 plus the vector force of 3 on 1. That's how we would write it, and these are both vectors, but since they're all lying in one direction along the x-axis, we can just call f of 2 on 1 negative and f of 3 on 1 positive, and we'll end up getting the magnitude, which will be a negative number, along the x-axis. In this case, using, if you remember, just reminding you of our I, J, K notation, the force would be in the negative I hat direction. And if we followed the same, well, no, let's skip that. Now, another situation that we could do the same thing for any of the other charges, right? Let's just try that. If we look at Q3, then both Q1 and Q2 are retracting it. So if we focus, if the question is, what is the net force on 3, it's going to be the sum of 2 forces. It's going to be the sum of the vector force of 1 on 3 plus the vector force of 2 on 3. Notice the convention, the force we're looking at is always written second. So let's draw those vectors in so we can see what we're looking at. The force of 1 on 3, what is that? That's an attractive force, because 1 is positive and 3 is negative. So that vector is going to be in this direction, and I'll call that f of 1 on 3. Well, 2 is also acting on 3, and it's attracting it, and it's much closer. So it's going to be much bigger. I'm going to erase this because the scale is going to be off. That force should be quite small compared to the second force. So let's put that back in as a very small vector. So when I draw the other vector, the force of 2 on 3, just from the diagram I should see it should be quite a bit bigger, even more than 4 times bigger, just eyeballing it. I'll make that a vector. And this vector is the force of 2 attracting charge 3. And I put the little vector sign over it. So you see, as a diagram showing the forces on Q3, we have those two forces. Down here, we have the equation that describes it. And if we were to write this out, what would it be? I don't want to write the whole thing out, but I'll start to write it out. The F13 would be K Q1 absolute value, Q3 absolute value over the distance between them. We'll just call that R13, and that has to be squared. That would give us the magnitude. But notice, if I want to make this a vector, the F13, you can see it in the diagram, it's in the negative I hat direction. So to actually make this a vector, not just a magnitude, I can put a negative sign here and an I. Well, I always write J instead of I. Let's erase that. I hat. So now this is written as a vector. Now you see what I've written over here is this term. I'm off the page, but if I wanted to continue and get the total force, I would write this term, and then we would put the numbers in. If we were given numbers, like values for those charges, we'd just put the numbers in and calculate it with the units. We'll practice doing that. But we'll also, in many cases, just have symbols. So let's say all these 3 charges are equal. And although it doesn't look like it, let's say the distances are equal. So that's a distance D, and this distance here, excuse the messiness, is also a distance D. Then in this case, the F13 would be K. Oh, and the charge magnitudes are all the same. This is equal to Q. This is equal to some value Q. It doesn't matter what it is, just that it's all equal. Of course, 1 is negative, so this would be K, in this case, Q squared over, now notice, I'm doing F13, so it's the distance from 1 to 3, and the distance from 1 to 3, the way I've drawn it, if you can see through the messiness of this drawing, is 2D. So that would be 2D squared, or you could write it as 4D squared. You're going to add to that the force of 2 on 3. So again, it's K. Since all the charges are equal, it's going to be Q squared. And now the distance from 2 to 3 is only a distance D, so this is D squared. So, doing the algebra, you can see that the KQ squared all factors out, and there's a 1/4 D squared and a 1D squared, so I'll leave it up to you to check my algebra. It's going to be 5/4 K Q squared D squared. This is, both of them are in the same direction, the negative direction. So I'm going to put a negative sign there, and then my I hat unit vector there.